Welcome to 5.3, Graphs of Quadratic Functions. We're going to use standard form, x-intercepts, we'll talk y-intercepts, and we'll go from there. Okay, so first of all, standard form of a quadratic is this right here, y equals ax squared plus bx plus c. To find the vertex, we can find our x value first. So our x value is equal to the opposite of b over 2a. All right, so looking at our standard form, and then to get our y value, we simply plug that x value back into our original equation and solve for y. So let's go ahead and get started with our first example. We're going to find the vertex, state it. We're going to find the y-intercept. We're going to find the x-intercept or x-intercepts, and then we're going to talk about symmetry points. All right, then we'll graph this quadratic function. So let's go ahead and begin. All right, the first example here, y equals negative x squared minus 2x plus 3. So if we want to find our vertex, we always start by finding our x value. So x is equal to the opposite of b over 2a. So in this case, the opposite of b is going to be 2 over 2 times our a value is negative 1. So we should get negative 1 for the x value. When we plug that back in to get our y value, we have the opposite of negative 1 squared minus 2 times negative 1 plus 3. So we get negative 1 squared is positive 1 times negative 1. It stays negative 1 plus 2 plus 3. So I believe we get y to be 4. So the vertex is the point negative 1, 4. So we'll highlight that guy. Okay. Next we need to find our y-intercept. So our y-intercept is, remember, when x is 0. So if we're looking at our equation here, our y-intercept should be easily identifiable. When x is 0, this guy goes away, this guy goes away. So really we're just left with our c value. So our y-intercept in standard form is always super easy to find because we're just looking at that c value, which in this case is 3. So we have the point 0, 3 for our y-intercept. Okay, so now we have to talk about our x-intercepts. Well, how do we find x-intercepts? Well, remember, x-intercepts can be found when y equals 0. All right, so we're going to set the equation equal to 0, and we're going to solve this. Now, since we're talking quadratics, we should look to see if we can factor it. So in this case, I'm going to first factor out that negative leading coefficient, and that just changes the signs inside. So now we can go ahead and factor this. Two numbers whose product is negative 3 adds to 2, and we get 0 is equal to the opposite of x plus 3 times x minus 1. And when we set those equal to 0, using our zero product property, we get two x-intercepts. X equals negative 3 and x equals 1. So I'm going to write those as ordered pairs. So we have the point negative 3, 0 and 1, 0. So there we have it. We have all of our information that we're talking about thus far. Now let's go ahead and put it into a table of values. Okay, so our vertex always goes smack dab in the middle of the table. So negative 1, 4 is our vertex, and I like to kind of highlight that, box it, whatever we need to do. And we can even label it with a V for vertex. Okay, so now we can plug in those other points. Well, we have the point 0, 3, okay, and we have our x-intercepts of 1, 0 and negative 3, 0. But one thing we haven't talked about yet is this symmetry point, okay? And what we should notice is that our x-intercepts, at least in this case, the x values are the same distance away from our vertex. So 1 is 2 units away from negative 1, and negative 3 is 2 units away from negative 1. So these 2 points happen to be symmetry points. So we can call those points of symmetry. can we find another one that is a symmetric point to our y-intercept of 0, 3? Well, 0 is 1 unit away from this x value of -1, so let's go in the other direction. So hopefully you recognize, oh, well, 1 unit away from -1 is going to put us at -2, and I should have the same y value there, 3. So symmetry points are equidistant from that x value. The x values are the same distance away, and the y values are going to be the same. Okay, so notice that aspect. Those y values are the same. Those are symmetric points, as well as these other y values. Those are also symmetric points. Okay, so hopefully we can recognize that. These are also points of symmetry here. All right? Okay, so now we can go ahead and graph these, or this parabola. We've got our vertex of -1, 4, and we can go ahead and plot those other points and get a good shape to our graph. So let's go ahead and zoom in. We've got the point -1, 4. We have the point 0, 3, and its symmetric point -2, 3. We have the point 1, 0, which is an x-intercept, and its symmetric point, also an x-intercept, -3, 0. Now we can go ahead and connect these nicely, and they've got a nice curve shape to it. And there we have it, our parabola. Let's take a look at example 2. All right, so first thing we need to do is find our vertex. So remember our vertex, we find our x value first. So x equals the opposite of b over 2a, which is -4 over 2 times -4, which comes out to be 1/2. So to find our y value, we plug that back in. -4 times 1/2 squared plus 4 times 1/2 minus 1. So 1/2 squared is really 1/4. Plus 4 times 1/2 is 2 minus 1. -4 times 1/4 is simply -1 plus 2 minus 1. And we end up with 0. So our vertex is the point 1/2, 0. What else do we notice about that point? Our y value is 0. So what else is that going to be? Okay, so let's think about that as we move forward. Next, let's find our y-intercept. So our y-intercept, again, is when x is 0, very easily found by looking at our c value. So when x is 0, we get our y to be -1. So there we have our y-intercept. Now, we need to talk about x-intercepts, right? And we already mentioned, hey, our vertex happens to be an x-intercept. Is that the only one? Well, let's think about the vertex, right? What happens at the vertex? That's where our graph shifts from increasing to decreasing, like that, or decreasing to increasing, where we're going to be opening up. Okay, now if we wanted to go through and algebraically find our x-intercept, we can certainly do that. So I'll do it over here. Our x-intercept, we would set our equation equal to 0, and we would go through and solve that. So I'm going to factor out that -1, and we're going to have 4x squared minus 4x plus 1, and this just so happens to factor as 2x minus 1 squared. So we end up with x equaling 1/2, right? There is only one x-intercept, which makes sense. Okay, so yes, we have the same thing. Okay, so when we're graphing and we're getting ready to graph and we're plugging into our table of values, our vertex goes smack dab in the middle. We have our y-intercept of 0, -1. We've already mentioned our x-intercept, so that's not going to help us with our table. So we need that point of symmetry. Okay, so our point of symmetry, well, I take a look, that is, 1/2 away. So then we have to go 1/2 away in the opposite direction. So that's going to give us an x value of 1. And since we know points of symmetry have the same y value, I know I'm going to have the point 1, negative 1. So this is our point of symmetry here. Okay, which is this guy right there. And now we can go ahead and graph with those 3 points. So I'm actually going to scale my graph a little differently so it's easier to actually graph. So I'm going to make each tick mark 1/2. Okay, and that way it'll be easier to graph. So when we do that, we have the point 1/2, 0, so there's where our vertex is. We go through the point 0, negative 1. Now I'm down here, remember, because we scaled each point as 1/2. And then I have the point 1, negative 1. So here we are, opening down, and there's a good look to our graph. I want you to try this last example on your own. Here's a clue. Your x-intercepts are going to take a little bit more work because you can't necessarily factor this. So see where that takes you. Go ahead, pause the video, try this problem, in completion, come back and check how you did. All right, so let's see how you did. You should have gotten the vertex to be -1, 4, opposite of b over 2 times a, and then we plug that back in to get the y value of 4. Our y-intercept in standard form is easily identifiable. It's that c value, so 0, 5. And then there is no real x-intercept. As you go through, you would try to factor it, but you can't. So you have to use that quadratic formula. So remember, the opposite of b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. And this comes out to be underneath, you'll get -16 underneath that radical. And as we go through, the square root of -16 becomes 4i. And then all 3 of these terms have a 2 in common, so we can pull that out and we get -1 plus or minus 2i. So graphically speaking, we can't graph those, so there's no real x-intercept. Okay, so as we are creating our table, we need to think about a point of symmetry. So our vertex is -1, 4, that goes smack dab in the middle. We have our y-intercept of 0, 5, which is the x value is 1 away from our vertex, so 1 away in the opposite direction gives me an x value of -2, and we know that our y value stays the same, which is 5. Okay, so this graph is going to open up. Go ahead, plot those points, and we get it here. So going back to this x-intercept, there is no real x-intercept, simply means that our graph isn't going to cross the x-axis, which is true. Our vertex is above that x-axis, and we open up, so we won't have any real x-intercepts. If you have any questions on this, make sure you ask in class. Have a good day.